slide, that slide was des arts.
Yeah.
Yeah, so, and she likes like animation.
Oh, okay.
Which I don't. I detest animation.
Probably another 6-7 minutes.
Bart would agree on that.
Who would agree?
Bart.
Yeah, yeah. Us old-fashioned types.
I think we had a talk like maybe about 2 or 3 years ago where we were debating about having a bicycle with the wheel spinning. Also, most people I think get static PDFs because when we distribute it, it's been distributed on the internet already.
Yes, right. Hi. What's your name?
Jody.
Hi.
Nice to meet you.
Nice meeting you.
I can hear him on the speaker already, on the webcam.
Not here, though.
Oh, inside.
Hi, hi, hi. See, nothing. Hi, 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 hi.
Be careful of those. You don't want like some
Test, test, test.
something like that.
I think I'll turn it off right now.
Well, welcome. Before we start the seminar, just a few housekeeping items. The restrooms are on the I Street end of the lobby, in case you need to use those at some point. If there is an emergency, take one of the exits and head to the main lobby stairs and proceed out the building. For webcast viewers, we're strongly encouraging you to send in your questions at your first opportunity so that we could have time enough during the Q&A and get them on the air. The address does show at the bottom of the monitor, sierram@calepa.ca.gov. So we're about to start. Dr. Wong?
Thank you, Peter. Is this on? Okay. It's my pleasure today to introduce today. Sorry, thanks. It's my pleasure to introduce today's California Air Resources Board, or CARB, research seminar titled "Toxicity of Source-Oriented Ambient Submicron Particulate Matter." My name is Pat Wong, and I, along with Ralph Plopper there, were the contract managers for this project. Before introducing our speakers today, I'd like to provide a little insight on why CARB was interested in this project and also how it fits in with CARB's mission. One of the central goals of CARB is to protect Californians from the harmful effects of air pollution. One way that CARB does this is to fund research projects in a variety of areas, including air pollution monitoring, health effects of air pollution, and new technologies, which could be reducing emissions of air pollutants. Through its efforts and verification through its monitoring program, air toxics and criteria pollutants have decreased substantially over the past few years. For example, statewide PM 2.5 since 1999, when monitoring began, has decreased 27%. A statistic made more remarkable by the fact that the population actually grew by 2 million people during that time. Despite this decrease in statewide ambient PM 2.5 levels, the map on the left shows that there are still non-attainment areas in California which do not meet the federal air quality standard for PM 2.5. So basically, there's still a lot of work to be done. One approach that CARB has taken is not to look just at the levels of PM, but the nature of PM pollution itself in identifying components which may be contributing disproportionate health risks when compared to others. In order to do this, we first have to understand how PM is formed. PM is often mentioned as a singular pollutant, PM-related studies, toxicology of PM, PM monitoring. But in actuality, PM is a mixture of particles of different size, shapes, and compositions. Part of this heterogeneity has to do with the fact that there are many ways for PM to be formed. A variety of sources, including vehicles, industrial, and natural sources such as agricultural and wood burning, can either release PM directly into the environment or release PM precursors, which can form PM through atmospheric chemistry. Regardless of its formation pathway, in published studies, all PM has some level of toxicity. The health risks of ambient air particles is fairly well established, and many studies have shown that this mixture of fine and possibly ultrafine particulates to be the most health-damaging components of ambient air. What is less certain, however, is whether or not the heterogeneous nature of PM formation leads to ambient air consisting of different types of PM, each with different levels of toxicity. Which brings us to the main objective of our study today, answering the question, do some PM in an ambient air sample contain chemical components that make it more toxic than others? And this project was broken down into two tasks. The first task was to develop methodology and instrumentation for the isolation and collection of ambient particulate matter from different sources and atmospheric processes. This was not an easy task. It involved building an innovative instrument to collect, analyze, and separate PM in a real-time basis based on specific chemical signatures related to different pathways and sources of PM formation. The completion of this task, in my opinion, was a major accomplishment, not just because of all the work that was involved, but the fact that we can adapt this technology to future projects. The second task of this project was to then explore the toxicological differences between these samples in an animal model. This task provided us not only with information on what PM chemical characteristics may be responsible for toxicity, but also an insight to the possible mechanisms of PM toxicity as well. Now, all our speakers today come from the University of California at Davis. Our first speaker is Dr. Tony Wexler, or Anthony Wexler, professor of mechanical and aerospace engineering, civil and environmental engineering, and land, air, and water resources. He is also the director of the Air Quality Research Center. He and his team are responsible for the design and implementation of the method and instruments for source-based PM collection. Our second speaker is Dr. Keith Bine. He is a member of Dr. Wexler's research team and is an assistant research scientist at the Air Quality Research Center and Crocker Nuclear Laboratory. He was responsible for much of the instrument construction, along with PM sample collection and preparation for the toxicity studies. And our final speaker today is Dr. Kent Pinkerton. He is a professor of pediatrics in the School of Medicine and professor of anatomy, physiology, and cell biology in the School of Veterinary Medicine. He is an expert in inhalation toxicology, and his research team is responsible for measuring the toxicity endpoints in the source-based PM samples. And I guess with that introduction, I'll turn the mic to you.
Thank you.
Sure.
Great. Can you, oh, yes, the mic works. Great. So good morning, or good afternoon. I guess we're in the afternoon now. Whoa, geez. So you see the title for the talk here, Source-Oriented Toxicity of Ambient, Fine, and Ultrafine PM. My colleagues, Keith Bine and Kent Pinkerton, were fantastic to work with on this project, and we made some nice breakthroughs. And I could not have carried it out without them, so thank you very much. And of course, thank you to the Air Resources Board and Electric Power Research Institute for sponsoring this, this wonderful partnership between industry and government. So the air pollution life cycle. So we emit particles from the atmosphere in, now if I get the cursor, there it is. We emit particles from the atmosphere. Those are the anthropogenic emissions. And then there are numerous natural emissions from particles in the atmosphere, from volcanoes, from sea spray, from many, many things. These particles then mix in the atmosphere. They react in the atmosphere. They can do phase change. That is, gases can become particles, and particles can become gases, or anyway, different compounds can move back and forth. And I just went on, and I shouldn't have done that. Sorry about that. And then these particles have their effect. Okay? So one classifications of effects are the health effects. That is, people inhale them, and then that affects their pulmonary system, or it did it again. Their cardiovascular system, or it can affect climate, another very important area of research. Okay, through these effects, these adverse effects, then that's where regulation comes into play. So regulations are then instituted to make sure that we minimize these adverse effects on health and climate and maybe other things. And come back, cursor. Oh man, this is going to be challenging. Okay. So anyway, the regulations then control the emissions, not the natural emissions, but the anthropogenic emissions. Right? We control those emissions, and then we have improved air quality, and we have fewer health effects and fewer climate effects. That's basically the sort of life cycle of air pollution in the regulatory environment. Okay, so one of the questions here is that this talk and all the work that we've done here is related to the health endpoints, not to the climate endpoints. And we're interested in sort of the relative toxicity of different particles in the atmosphere. And this is a challenging topic because we need to be able to figure out where the particles came from in the atmosphere. So the question is, are all the particles created equal, or are some particles more equal than others, as George Orwell would have said in Animal House, his famous book. And so as an example, do we expect that sea spray and diesel exhaust should have the same toxicity? Well, no. On the other hand, the National Ambient Air Quality Standards regulate mass, total mass, and so they're really all treated the same. And there's good reasons for that. It's easy to measure total mass. It's easy to do epidemiological studies on total mass. Separating things out from their sources or their compositions is expensive. So it's very hard to do that on a large national network. So how do we deduce the health effects from different sources? You can do this either epidemiologically or toxicologically. Epidemiologically, you can look at people who live in high-risk areas, such as near freeways or downwind from a major source, like let's say a coal-fired power plant. And do those people who live in those places have different health endpoints? Do they have higher risks for certain diseases because they live in these areas that have a higher air pollution load? Okay, but those are correlative, not causative. That is, we see associations between them. We don't really know what's going on behind the scenes. And because many things correlate with each other, it's not clear exactly what the cause and effect is. And that's what we're looking for here, causative. So the other way of approaching this problem is toxicologically. And so the question is, how can we take particles and expose them to, say, animals or people and find out what their toxicity is? So some difficulties there are, how do we deal with those nasty secondary compounds? And so for those who don't know the terminology, there are primary and secondary compounds. The primary compounds are compounds that are in particles emitted from sources right when they're emitted. And the secondary compounds are those particles, or those compounds, excuse me, that are emitted as gases and eventually make their way into particles via chemical mechanisms or whatever chemical processes in the atmosphere. Second question there is, how does the atmosphere potentially change the toxicity of emissions? We can certainly take, say, animals that we'd like to expose and do toxicological work with and expose them to direct emissions from sources. But it's not clear that direct emissions from sources really represent the true toxicity of what we breathe in the atmosphere. People don't hang around with their mouth over the tailpipe of a car. At least we hope they don't. They burn their lips. Okay? So the issue is the atmosphere may be changing the toxicity of emissions in either way, either making them more toxic, making them less toxic, or making them toxic in different ways altogether than what was directly emitted. So really what we'd like to do is to be able to collect particles from the atmosphere that are associated with particular sources, because that's truly the kind of air pollution that we breathe when we're walking around and living our lives. So the problem there isn't the atmosphere well mixed? Well, if we measure particles in the atmosphere over the course of hours and days, which is what commonly is done, the answer is they're pretty well mixed on that time scale. But if you can measure particles on a very, very short time scale, on the order of some minutes, substantially less than an hour, then the story is different. And we find that the atmosphere is not very well mixed on those short time scales. And so by using that paradigm, we hope to be able to separate out, and in fact we did separate out, particles in the atmosphere from different sources related by doing things fast. Okay? So that's the short introduction to what's coming up. Now there are 4 different sections to this talk. The first section is my responsibility, and that will be basically how did we sample PM out of the atmosphere in a source-oriented way. And so I'll talk about the instrumentation and some of the ideas behind how we did that. The second part of the talk will be given by Dr. Keith Bine, and it will be on source attribution. What that means is we collect particles out of the atmosphere, and we think we know what sources they're associated with because of how we programmed all of our computers, which I'll get to, but we need to confirm that. Okay? And so Keith will talk about how we confirmed that in the study that we just did here. The third part of the talk will also be given by Dr. Bine, and that has to do with, now we've collected all these particles on filters, and we need to extract the particles from filters into a medium that toxicologists, that is specifically Dr. Pinkerton in his laboratory, can use to test their toxicity. And so a lot of effort went into figuring out how to get those particles off those filters in the most faithful way possible so that we are doing a very fair attribution of toxicity to the different sources. And then finally, those particles were tested for their toxicity, and Dr. Pinkerton will then take over the podium at that point and talk about toxicity of different sources that we found. Okay, so let's talk about the not well mixed part of this. So some years ago, Murray Johnston at the University of Delaware and I, when I was there also as a professor, we developed instrumentation for measuring the composition of particles in the atmosphere one by one in real time. So this instrument sucks particles in, it sizes the particles, it does chemical analysis of them individually, particle by particle, in real time, that is instantaneously. The particles come in, they're zapped, we get a mass spectrum, we know what the particles are made of. Okay? Now we've operated this instrument or its close cousins in 4 different cities around the country before we did this project. That is in Atlanta, Houston, Baltimore, and Pittsburgh as part of the EPA SuperSite program, which was going on some years ago. And from that, we see that over the short time scales that we can access with something like a single particle mass spectrometer, the atmosphere is not actually that well mixed. Okay, so what's the big idea? So the idea is to run the single particle mass spectrometer in the atmosphere to characterize the mixing state. That is, what sources are coming individually, what sources are coming together to the site, and to characterize that sort of temporal evolution of particles in the atmosphere as they come to the site. Okay? We do that in order to then figure out what's really possible with the site we've picked in the atmosphere in the city that we're sitting in, and what can be separated out. Okay, then we're going to take 10 different high-volume samplers. These are samplers that are invented by folks at Harvard University. They sample particles out of the atmosphere size-resolved, and they run a large volume of air through them because we can collect a large mass of particles that way. And we need a large mass of particles, relatively speaking, in order to do our toxicological tests. So what we do is we then assign different kinds of sources to the different ChemVol high-volume samplers in our software, which I'll get to. We use the single particle mass spectrometer then to see what's going on in the atmosphere at a given time. When we see that the particles are of a certain composition, we know we have an association between that composition and a particular source. We've assigned that particular source to a ChemVol, so we turn that ChemVol on. And we sample out of the atmosphere until the single particle mass spectrometer sees new particle compositions in the atmosphere. Then we turn that one off and we turn a different one on to sample that stuff now. Okay? And over the course of weeks, we then collect enough material for the toxicological studies. Okay, so here's a schematic of what's going on. Now, here's first I want my cursor. Hello, cursor, anybody home? Oh, come on, there it is. Okay, so here's part of California. This is the San Joaquin Valley, and you can see some fog or maybe smog in the San Joaquin Valley of California from a satellite photo. And what's contributing to that are various things. We have, for instance, we have exhaust from vehicles. We have someone barbecuing here, if you can hardly even see who they are. We have people who are burning wood to heat their homes. We have various industrial and power plant processes that are emitting pollutants into the atmosphere, and many, many other things too. Okay? So what we do is we get our cursor back eventually, someday, maybe, there it is, and we look at what's going on in the atmosphere. Now this stuff is all well mixed, or anyway, we thought it was well mixed. Anyway, it's all mixed into the air pollution that's in the San Joaquin Valley. We look at that with our mass spectrometer, and there's a computer here, typified by a brain, okay, that is going to look at the signals coming out of the mass spectrometer. It's going to look at the particle compositions. That computer is then going to energize valves that are going to direct the air pollution that we thought was well mixed into different buckets. And here's the bucket for the exhaust, and there's the bucket for the poor guy who's barbecuing, et cetera, et cetera. Okay? So basically, we're just turning on different valves and directing the air pollution to different buckets. That is the ChemVols that we talked about before, the ChemVol high-volume samplers. And therefore, we're going to be able to collect source-oriented PM. Here's a schematic of the same kind of thing. We have a stack here, which brings in air from the outside. The stack is some number of feet above the site, so we don't have anything that's very local. Don't do that to me. Thank you very much. We get rid of the particles that are larger than 1 micron in some pre-cut ChemVols. This goes then into a manifold, just a big duct. Okay? And sucking off that duct are various ChemVols. These are the ChemVols here, and there are 10 of them. And again, they're all assigned in software for different sources. Okay, so now there is a single particle mass spectrometer that's called RSMS2 here that looks at what's going on in the atmosphere, also taking particles out of the atmosphere, looking at what the current composition is of the particles in the atmosphere, and then controlling which of the ChemVols is on at a given time. Okay, then air is then sucked out of whichever one it's flowing through and goes to a pump and is discharged back into the atmosphere. Here is a technical drawing, CAD drawing of the different components of this instrument, how we laid them out inside our trailer. Cursor, please come back. There we are. So here's the RSMS2 single particle mass spectrometer. It had its own stack at the same height as the stack that was drawing particles into the chem-vols. So air was drawn down here into the single particle mass spectrometer, which then looked for their composition as a function of time and figured out which one was which with computer control and computer smarts that Keith painfully programmed in. Here is the array. Here you can see there's two different rows of these things, one row here, one row here. These are the chem-vols, and here are the two different sampling stages, right there and right there. Okay, here are the valves I talked about, and these are then controlled by the computer that also controls the single particle mass spectrometer. So air then comes down here, routes around here inside the trailer, and then it's directed through manifolds here and down into the chem-vols. Here's a picture of the single particle mass spectrometer. Again, there's the cursor. So here is the computer screen for the computer that did all the thinking. These are power supplies. Here's the mass spectrometer time-of-flight tube, a bunch of valves and conditioning equipment, and here's a bunch of vacuum stuff to keep the whole thing clean. And down here are lasers. The purple box is a laser that hits the particles with a high-energy pulse of high-energy photons, which then ablate and ionize the particles for the chemical analysis. And the other side of the trailer, so on this side over here to the right was where the single particle mass spectrometer was. You can see just a little bit of it in this photo and a little bit of it in this photo. On the left side of the trailer were the chem-vols, and here's the manifold I talked about here. Here's the different chem-vols and down here. Down here are the valves I mentioned before that are all controlled by the same computer that controls the single particle mass spectrometer. And here's the ducting that you saw the schematic of all outside. Here's the stack for the chem-vol, and here's the stack for the single particle mass spectrometer. Okay, so then what we do is we see that there are a bunch of different kinds of particle emissions or particle types that are in the atmosphere in Fresno. And if we went to a different location, we would see something different. And even in the same location in a different season, we see things that are different, somewhat different. Okay? So what we do, first of all, is we run this instrument for a few weeks ahead of time to kind of characterize the mixing state of the atmosphere. Then we program which of the different chem-vols corresponds to different sources. And then we run it to actually collect the stuff. So if you look here, you'll see that in Fresno, we saw roughly, again, where's my cursor? There it is. We saw roughly 42 different major kinds of particle compositions. We call that cluster number. So we have basically 40 different kinds of particle compositions. In this case here, so what happens is that when you're sitting at a site and measuring, you see particles that may be dominated by one or two different sources. Okay? In this case here, we saw, after running for some time and waiting for the cursor to come back, we saw that predominantly the particles came from a source that had a large potassium signal, which is indicative of biomass burning. Okay? And the other sources were very small. In contrast to that is another kind of particle class that we saw, which is indicative also of biomass burning, but biomass burning that has more secondary components. That stuff has been around in the atmosphere for a longer period of time and has had a chance to have other things condense on it or reactions to happen that change its composition. So here we see some of those pure emitted particles. We also see some other particles that are more complicated, that have organic carbon, ammonium nitrate, elemental carbon mixed in with them. Okay? So when we're collecting with these chem-vols, we're collecting these kinds of things. Sometimes they're primary sources, like just the biomass burning, like you saw in the previous slide. Sometimes they're mixtures of particles that still indicate something that's going on in the atmosphere, like in this case, a more processed kind of particles in the atmosphere. So one question is fidelity, which is, well, okay, we had this goal of collecting different things in different chem-vol samplers. How well did we do? So the gray bar in this slide is our goal, right? How much we were planning on collecting in the different chem-vols. And the red bar is actually what we did. And so you can see that the composition mix, where's the cursor? There it is. the composition mix is pretty good. So you can see these matched up pretty well, but it's not always. Once in a while we didn't get things quite the way we anticipated, okay? But you can see there's, for both the summer season, we did this work in 2 seasons to catch that seasonal difference in Fresno. But you see that for both seasons, there's a pretty good match between the mix of particles associated with each chem-vol that we anticipated and what we actually found. Okay, so in summary, we collected source-oriented particles from the atmosphere in Fresno. We did it for 2 seasons, the summer of 2008 and the winter of 2009. We did it in 2 different size ranges. One size range was from 0 to 0.17 micron, or 170 nanometers. That means the same thing. And the other size that we took, we're going to call that submicron fine. It is between 170 nanometers and 1 micron. Okay, so you're going to see these terms again throughout the talk of ultrafine, which is that 170 and smaller, and submicron fine, which is 170 nanometers to 1 micron. Of all the different, so we had 10 chem-vol samplers running in the summer and 10 running in the winter. And some of the sources are very frequent, and some of the sources are very infrequent. And we tried to run them long enough so that we had enough material for the tox studies from even the most infrequent sources. Okay? We didn't always succeed, okay? But we did very well. So from almost all the sources that we tried to collect, we accomplished enough material, we collected enough material for the tox studies to represent the mix of PM in Fresno. And we had good separation, as I showed you, and there's other statistics that show we had good separation between the different sources. Not complete separation, but good separation. Okay, so to continue with the talk presentation, as I said before, there are 4 different parts of this talk. The next 2 parts will be given by Dr. Keith Bine. He'll talk about source attribution first, then the PM extraction methods that we used, and then he'll move on, and then the talk series will move on to Ken Pinkerton, who will talk about the source-oriented toxicity.
Hello, everybody. Thank you, Tony, for that wonderful introduction on what we did and how we did it and why we did it. My name is Keith Bine, and I will be giving the next 2 sections of this presentation. The first one is going to be source attribution. So now that we have collected our sample in different buckets, we want to attribute those different buckets or chem-vols to different sources. This is something we actually did not do during the sampling. This is done after the sampling, and the reason for that I'll explain right now. So we made chem-vol assignments based on differences in particle composition, based on we measured with the single particle mass spec. And the fundamental idea is that different sources tend to emit particles with different composition. So if we run our sampling based on different chemical compositions, this is synonymous or analogous to collecting samples based on different sources. So the way the sampling works is we go out in the field or set up our sampling site and we run a pre-study where we run only the single particle mass spec by itself. And we do this to characterize the composition of the airshed. We want to know what kind of particle types are out there. What do they look like? How frequently do we see them? What combinations do we see them in? And then we use this data to make assignments, and we assign different particle types to different chem-vols. After this pre-study, then we go out and we actually do the sampling. And we want to make the turnover between the pre-study and the actual sampling as quick as possible so that the composition of the atmosphere doesn't change. The trends we saw in the pre-study can still be used to guide the collection and sampling during the actual sampling campaigns. So there's not enough time to do a full comprehensive source attribution study between the pre-study and the sampling. So now what we're doing is we're going back after the fact and saying, well, how well did we do? How well did we separate the sources based on differences in chemical composition? And that's what this part of the talk is going to be about. So obviously we have particle composition, which is a good source attribution tool. Other than that, we have a few other tools available to us. One very important tool is determining the site-source relation. That is, what are the major sources surrounding our site, and what is their location geospatially relative to our sampling site. So on the left-hand side of the screen, these are various Google Earth images at various spatial scales. The first one is the close-up. It's labeled A. There's my cursor. And this little red dot actually shows our sampling site. It is located in the rear parking lot of the UC Center on Shaw Avenue in Fresno. And that little white building by the red dot is actually the UC Center. The main drag going across the picture is Shaw Avenue. And that's California State Route 41, or the Yosemite Freeway, going up and down. Immediately across the street, we have a large shopping complex. It has various fast food restaurants, restaurant chains. And immediately behind the sampling site, we have a huge residential area directly behind and to the northeast. If we step out, if we zoom out one level, you see more of the commercial and shopping sector along Shaw Avenue. Again, these are mainly restaurants and fast food chains and different variety shops. You also see a large commercial sector that is parallel to the Yosemite Freeway. Again, various shops and restaurants and fast food chains. And then you get to see the residential sprawl, and the entire site is surrounded by residential areas, so that one of the biggest local inputs to the air pollution is going to be residential activities. It's going to be heating, cooking, driving, these kinds of things. And then if we pan out even further in the bottom left-hand corner, you get to see the boundaries of Fresno, and you get to see the start of agricultural lands in different surrounding cities like Clovis. And take a step out even further, you see the beginning of the foothills, the width of the San Joaquin Valley, and you see that Fresno is surrounded by agricultural lands. And agricultural-related activities are going to be one of the larger regional source inputs into the airshed, and this will constitute a large fraction of the background PM that we see in Fresno. In the right-hand side, I list some of the emission sources in more detail. At the local scale, we have vehicular emissions. This is going to be a combination of gasoline and diesel-powered vehicles operated under a wide variety of different operating conditions, cold starts, idling, low to high-speed operation on freeways, commercial streets, residential roads, and even parking lots. Another local scale source is going to be residential and commercial cooking. You have barbecuing, pan frying, flame broiling, deep frying, all these different sources of particles. You have space heating. These could be fireplaces, wood stoves, pellet stoves. Could be gas or propane-powered heaters, something like this. And then you also have construction and landscaping. For landscaping, you'll have two-stroke motors of lawn mowers, leaf blowers, trimmers, hedgers, these kinds of things. For construction, you have diesel trucks bringing in supplies. You have generators supplying power. You have gasoline and diesel-powered construction equipment, backhoes, dozers, these kinds of things. And then stepping out to the regional scale, we'll have agricultural-related emissions. Ranching, this is predominantly associated with gas-based emissions, ammonia and methane and things like that. There'll be important components of secondary processing that goes on in the atmosphere. For agriculture, you'll have agricultural machinery. Again, these are mostly diesel and gasoline-powered machinery where you have trucks, off-road vehicles, tillers, holers, you name it. And then during certain seasons, you'll have waste and debris burning. This will be a biomass combustion signature. Then you also have the product transportation infrastructure, which is going to be largely diesel trucks coming in, picking up, distributing to other areas. Also on the regional scale, you'll have atmospheric processing. Tony talked about this a little bit. But basically, particles and the gases in the atmosphere are photoactive, and they react to form different components when they're subjected to the sunlight. And this changes the mass of PM in the atmosphere, it changes the composition of PM, and so it's an important source of particulate components. And lastly, well, I should mention for the San Joaquin Valley in general and Fresno, specifically the biggest secondary components that are going to be of concern are going to be ammonium nitrate. This typically comes from a mixture of ammonia from cattle ranching and NOx emitted from vehicular emissions, and then what's called SOA, or secondary organic aerosol. And the basic idea there is small, highly volatile gas phase organics undergo reactions. They become larger, less volatile, and eventually they condense into the particle phase. This increases the mass concentration of particulate-bound organic carbon as well as changes the chemical composition. And lastly is long-range transport. Important for Californians is going to be wildfires and maybe even trans-Pacific transport from Asia, most notably China. However, long-range transport tends to be very episodic, only happening when the conditions are just right. So on a day-to-day basis, long-range transport is not going to be as important as the local sources and the regional sources. So our next tool is directional relation. And so we think about how are the particles in the atmosphere moved around, how are they transported. And obviously this is meteorological. They're driven by wind direction, wind speed, and atmospheric stability. Well, the easiest source attribution tool for us to apply is wind direction. And the wind direction tells us what direction the emissions that are impacting our site originated from. And if we can use that directionality with the knowledge of what sources are over there, we can get a good idea of what sources are emitting the stuff that we are collecting. And so what we're looking at here are actually polar graphs. They're frequency distributions, and we're looking at the frequency with which the wind was blowing from a certain direction while we were sampling into a particular chem-vol. So basically, while we're sampling in a chem-vol, we're counting wind observations as a function of wind direction, and then we plot this. And so if certain chem-vols are highly correlated with a specific wind direction, then this is a strong indicator that we're doing a good job of separating sources. And that's the main thing I want to show with this slide is, number one, individual chem-vols are indeed highly correlated with specific wind direction. This is for both the summer on the left and the winter on the right, and the different panels show different chem-vols. And number two, different chem-vols are generally associated with different wind directions. Again, this is showing us that we did a good job separating sources into different chem-vols. As some specific examples, chem-vol 1 from the summer has been attributed to residential cooking, and we see that these emissions predominantly originate from the northeast quadrant, and this is where the large residential area immediately behind our sampling site was. And so this is the summertime, and we postulate that a lot of these are actually barbecue-related emissions coming from the backyards of this large residential area. Another example is chem-vol 3, which we have attributed to vehicular emissions. And we have a strong wind signature pointing to the west, and that's where the California State Route 41 Yosemite Freeway is located. Similar kinds of arguments can be made for the winter wind directional signatures. And the last tool that we use is temporal relation, and we're looking at the temporal trends of when we are sampling into particular chem-vols. The basic idea is that certain sources are known to emit during certain times of day. A classic example is traffic. We know that traffic is heaviest in the morning and evening rush hour commutes. So if we see this signal in our data, then we have further evidence that we are doing a good job separating sources. And so similar to the wind direction data, the main point to be made here is that if different chem-vols are correlated with different times of day, then this is another strong indicator that we are separating sources into different chem-vols. So perhaps some of the most dramatic differences are between chem-vol 1 and 2 for both the summer and the winter. For the summer, like I said before, ChemVol 1 is associated with this residential cooking. So the amount of ChemVol sampling begins to increase around dinner time. Well, I should note, the x-axis scale doesn't go for the full 24-hour cycle. It starts at about, this is military time, it starts at about 1500, about 3 p.m. On one day, and it goes through till about noon on the next day. And this is for our entire sampling period. It's not just one day. We're summing over all sampling times for the entire sampling period. And that we see, so back to ChemVol 1, the residential cooking, it begins to increase around dinner time, around 6 p.m. It continues to increase through the dinner time hours. It plateaus in the late night hours, and then it begins to decrease in the early morning hours. As it begins to decrease, we see that ChemVol 2, which has been attributed to a highly processed regional background PM, begins to increase. The basic phenomenon going on here is the development of a nocturnal inversion. The inversion breaks in the morning, and whatever was caught aloft from the night before mixes down. So at the nighttime, what an inversion does is it caps the atmosphere. It suppresses mixing. So sources are emitting into a smaller volume. They are not being mixed. They may be moved around slightly by breezes, but they're not mixed up. And so we get pretty clean source signatures at night due to this lack of mixing. And then when the sun comes back out, starts to heat up the ground, the atmosphere, the inversion breaks. Whatever's above, the inversion gets mixed down, and this is the highly processed regional background trapped from the day before and perhaps transported around. And we see that happening both in the winter and the summer for ChemVol 1 and 2. And similar to the wind direction analysis, the main point here is that particular ChemVols are associated with particular times of day, and different ChemVols are associated with different times of day. This indicates that we're doing a good job separating sources into different ChemVols. Finally, this is the culmination of our source attribution effort. I call it the ChemVol source combination reconciliation. On the very left-hand column is all the different ChemVol numbers. We have 2 columns for the summer of 2008, 2 columns for the winter of 2009. The first column is the dominant particle types that we used to attribute different ChemVols to different sources. I'll explain that in just a second. And then the second column are the dominant sources that we've assigned to these ChemVols based on the particle types, based on the wind direction analysis, and based on the temporal analysis. So for the dominant particle types, K stands for potassium. Potassium is commonly an indicator of biomass combustion. It's one of the macronutrients found in all biomass, and as you burn it, it has a very high volatility relative to the other metals. It tends to vaporize and condense nucleate form ultrafine particles. CAN stands for carbonaceous ammonium nitrate. And this is the presence of elemental carbon, EC, organic carbon, OC, and ammonium nit together in individual particles. And it's the presence of ammonium nitrate that is an indicator of atmospheric processing. EC stands for elemental carbon, and we see particles that are predominantly elemental carbon in composition. And we tend to attribute these to diesel more than gasoline-powered emissions. CAN, I already did. K is potassium. ECOC are particles that show both elemental carbon and organic carbon, again, together in individual particles. Metals, that's a big mixture of different metals that we found in these particles. There weren't enough observations to split them out into different ChemVols, so we kind of tried to lump them all together in one ChemVol that has higher concentrations of metals. Na and K is sodium and potassium together in individual particles. First column on the right-hand side, the potassium ECOC. This is potassium, elemental carbon, organic carbon, again, all observed together in individual particles. This is the classic source signature of biomass combustion for flaming wood combustion, wildfires, fireplaces, campfires, stuff like this. CAN, we did EC, ECOC, and that's pretty much it. So for the dominant sources, we have cooking emissions, both local residential as well as commercial. we have highly processed regional background PM containing a lot of organic carbon, ammonium nitrate. We have vehicular emissions of various mixtures of diesel and gasoline-powered combustion emissions. We have certain chem-vols that were mixtures of different sources. For instance, chem-vol 4 from the summer and chem-vol 5 from the winter. We also have chem-vols that were timed. That is, they were timed to sample in a particular time window every day, and they did it in the same time window every day. Most notable would be chem-vol 9. Chem-vol 9 was configured to sample the daytime mix layer. And the reason we did this is that on average, the atmosphere is the most mixed during the daytime. And we have to put in the most energy for the littlest return trying to do source-oriented sampling during the daytime. So to save wear and tear on our instrument and costs, we decided we would just sample through one chem-vol during the daytime and do all source-oriented sampling during the nighttime. Chem-vol 8 in the winter is another example of a timed chem-vol, and we timed this to try to connect, that's wrong, but try to catch the morning commute. I apologize, the time is wrong on that. I believe it's sampled from 7 in the morning to 9 in the morning. And chem-vol 10 is what we call this undifferentiated chem-vol, and what it kind of represents is the nighttime mix beneath the nocturnal inversion. It's pretty much the analogy of chem-vol 9 in the daytime, except it's the nighttime. The reason we have this chem-vol is that when we're doing our source-oriented sampling, there's going to be times that we don't recognize what's going on in the atmosphere, or it doesn't match one of our pre-configured atmospheric states that we've associated with different chem-vols. So when that happens, we switch to chem-vol 10, and we sample in that chem-vol until our sampling algorithms re-recognize what's going on, and we can switch to a different source-oriented. So that's basically what chem-vol 10 is. It's kind of this nighttime nocturnal mix, and that's so these are our sources, and these are our source attribution analysis, different sources for the different chem-vols, and this is what we're going to look for as far as differences in toxicity. So next, we've collected our sample in our buckets. We've done our source attribution. We know where the PM that we collected in the different buckets came from. And now we need to remove the PM from the bucket so we can give it to the toxicity people to run their tests. So that's the question that this next section of the talk addresses. How do we get the PM off the filters? So first of all, it's important to understand how we remove the PM from the atmosphere. We do it by filtration. We run large volumes of air through filters. Gas molecules go through, the particles impact, and are retained by the filters. So we have filters that have all kinds of gunk on them. And we need to get this gunk off in some way. And we need to do it with some conservation objectives in mind. We want to try to recreate the PM as we sampled it from the atmosphere. And the issue is that different PM components have different properties. For example, water-soluble components are pretty easy to get off the filter if they're water-soluble, and you could just put them in the water, they come off. Other PM components are very sticky. Organics, pHs, these things have strong cohesive forces with the filter. They're hard to get off. They're insoluble with water, and additional steps are required to remove this material. And so what are the main objectives? And this is obviously to conserve the physical and chemical properties of the PM. Like I said, we want to try to recreate the PM as it was when we sampled it. Different things include size distribution, particle size, particle morphology, single particle integrity, these kinds of things. But are these reasonable objectives? And if not, what are the reasonable conservation objectives? And it turns out that the physical integrity is essentially lost during the actual impaction process. You're bringing particles onto a filter, you're impacting them at very large phase velocities, and there's high collision energy, and these particles tend to aggregate, stick together, and when you try to remove them, it's not possible to recreate the exact size distribution or particle morphology that was out in the atmosphere. So what we try to do is we try to focus on conserving the total mass that we collected on the filter, and B, conserving the total bulk phase chemical composition. What is the current state of science on extracting filters? Interestingly enough, this is kind of its own field of study, and it's more along the line of a separation of science than anything else. But there are numerous standard operating procedures available. Different groups use different SOPs, and some of the bigger problems is that A, at least to our knowledge, there are no published validation studies on any of the individual SOPs, and more importantly, again, to our knowledge, there are no intercomparison studies that have been published looking at different SOPs. And the issue here is that we have to ask, well, are different SOPs eliciting different toxicological responses? And this may even depend further on the toxicological endpoint that we look at. And we tested and tried a lot of these SOPs, and we found a lot of concerns along the way about different artifacts that may be introducing large errors into what we're getting. So what we did is we developed a new method for our own study to address some of these issues. And some of these issues include extraction efficiency, how much mass is being removed from the filter. Compositional biases, are we removing some PM component but not removing others? Evaporation losses, when we remove whatever medium we are removing our particles from the filter into, we have to get rid of that medium, that solvent. When we do that, are we also removing some of the PM components? Contamination factors, are we introducing filter material into our samples, and is that going to affect toxicity of the sample? And so these are our objectives. First and foremost, we want to maximize the extraction efficiency. This is how much PM are we pulling off of the filter relative to how much PM we actually collected on the filter. And this is unique to source-oriented sampling, like Tony mentioned. Some sources are more difficult to collect than others. And these difficult sources means we have a limited capability in how much mass we can collect. So we need to be very careful that we pull as much mass off the filter as possible so that we can do toxicity testing on these more rare sources. Secondly, we want to minimize compositional bias. This is analogous to conserving PM composition. We want to make sure that we're pulling all of the PM components off the filter. We don't want to leave some on while we take others off, because this is going to bias the composition of the PM when we do our toxicity studies. Next, we want to minimize extraction artifacts, like I mentioned, evaporation and even condensation. And finally, we want to minimize any possible sources of contamination, and predominantly we're talking about filter material here. So what are our new approaches? Excuse me. So if you want to maximize extraction efficiency, there's really no way around using ultrasonic sonication. And basically what you're doing is you're using sound waves to remove the particles from the filter. And this is a mechanical process. It's actually the energy of the sound waves, the cavitation energy, that is breaking the adhesive and cohesive bonds, holding the particles together into the filter. So what is traditionally done in most of the common SOPs is a water sonication, and they only use water. And that takes off a good fraction of the PM and all the water-soluble components. And it's very common for people doing these kinds of SOPs to report extraction efficiencies on the order of 70%. Our concern is that 30% remaining on the filter, and obviously it is compositionally biased. The water's not removing it, means it's insoluble in water, or perhaps it's showing excessive cohesive forces with the filter. So what did we do is we introduced sonication with additional solvents. We used water, and then we selected an intermediate polarity organic solvent, dichloromethane, and we introduced a nonpolar organic solvent, hexane. And these go in, and they do a really good job of removing the remainder of these components. And an added bonus is we picked these particular solvents because they're so volatile, and they readily evaporate at atmospheric conditions. They're easy to get rid of, and so we don't run into the problem of losing PM components while we're trying to remove all solvents. And so recovering the PM from the solvents, if you're going to do sonication, you need to do it in a medium to support the sound waves, A, and B, to collect particles once they come off the filter. You need to recollect them in a medium. So how do you remove the solvent from the PM, almost all of the current SOPs that are commonly used use lyophilization, and this is a fancy word for freeze drying. Basically, you're freezing your samples with your particles in it to a very low temperature. You subject it to vacuum. The ice sublimates directly from solid to the gas. It removes all of the water and just leaves you dry PM and your vial. And the problem there is that water is pretty stable in the liquid form with respect to evaporation compared to other PM components that we find. For example, volatile and semi-volatile organics. So if you're subjecting your samples to fairly harsh conditions like lyophilization, you're likely removing a substantial portion of your volatile, semi-volatile organics, other things like ammonium nitrate. So for the additional solvents that we introduced, we used evaporation, and we do this under a nitrogen atmosphere to eliminate any potential contamination sources as well as speed up the process. But you could also do distillation, and the added benefit there is that you further increase the speed of the process as well as you allow solvent recovery. And the solvents can be cleaned up, reused, reduce waste, reduce cost. So the next thing we introduced was called solvent washing. And this is based on the concern that some of our PM components are going to be evaporated during the lyophilization process. So what we do is we use our high volatility immiscible solvents. We go in and we will wash all the particles that are in our water, and we try to pull out those organic components into our organic solvents, remove them prior to the lyophilization process. We can blow down the organic solvents, recover organic fractions, add them back in to the other PM after the lyophilization. And our last step is called selective filtering. And the issue here is that when you use ultrasonic sonication, there's no way around breaking up some of that filter material and getting it into your sample. When you remove the solvents, it's going to be left in your sample. So contaminant filter material typically shows up as micron to millimeter sized filter fibers. So what we use is we use a selective filtering technique. We use microporous membrane filters of a known pore size. We pick the pore size that's large enough that all our smaller particles go through, and the larger fiber filters get retained. We obviously can't remove everything. If we make the pore size too small, then we're going to start removing particles from our sample as well. So there's some give and play there. And lastly is a very important question of how much PM do we have. PM mass is used as the normalizing parameter for all toxicity testing. So it's very important to provide accurate and precise mass measurements. What is the problem is that we typically are subtracting two very large numbers to get a very small number, and there's a lot of measurement error within that process. And why is it important? Like I said, there's dose-response studies, there's intercomparison studies, and there are two methods to do this. Traditionally is the filter difference method. You weigh your filter before you extract it, you weigh your filter after you extract it, you use the difference as a metric of the mass that you've extracted. One of the biggest problems here is you're not directly measuring the PM mass. So you're not accounting for any potential losses that are happening as a result of the extraction process. Additional process problems or measurement errors arise for properties of the filter. This is static charge or water absorption. And these are big issues and can introduce large measurement errors. So what we did is we actually do a direct measurement. This is still a method of differences. We are pre and post weighing a vial, but in this case, we are directly measuring the dry PM in the vial, and it accounts for all the potential losses that arise from our extraction process. And we minimize some of these additional artifacts for a direct measurement that is less prone to measurement error. So that's what we did. And now we can look at some results. This is looking at our new extraction method applied to the filters that we use to collect the ultrafine fraction during our winter campaign. On the x-axis are the different ChemVol numbers. On the y-axis is the breakdown of the total extracted PM mass that we recover during each step of our extraction process. So these bottom three bars represent roughly what would be removed if you used what's out there, the most common SOPs currently available. It's roughly around 70%. The top two bars represent the additional mass that we extracted by doing additional sonications in different solvents. You see across the board, we've increased our extraction efficiency on the order of 15 to 30%. This is compositionally specific because these are the components that water didn't remove. So we have, I think, conserved chemical composition a little bit better than these SOPs, and we definitely have a better extraction efficiency. And we can look at the same thing for the substrates that we use to collect the submicron fine PM during the winter. We use different substrates to collect the ultrafine and the fine. The ultrafine, we use Teflon-coated glass microfiber filters, pretty standard. For the submicron fine, we use polyurethane foam substrates. Different filters and substrates require different extraction protocols. So the extraction protocol we used for the submicron fine was a little bit different. And again, it's the same setup. X-axis are the different chem vols. Y-axis shows the percent breakdown of the total extracted PM mass by step. Again, the bottom three bars show roughly what you would get using the most common SOPs out there. The top three bars in this case, encircled by the red oval, show you the increase in extraction efficiency that we obtained with our new method. Across the board, you're seeing a 20 to 50% increase in extraction efficiency. And the final slide that I will show you today is gravimetric analysis. How well are we measuring mass? So on the x-axis, you have the different chem vols. For each chem vol number, you have 4 different points corresponding to 2 different size fractions for 2 different seasons. On the y-axis, you're looking at the percent difference between what I call the component sum and the total extracted PM mass. So as we go through our extraction process step by step, we actually weigh the amount of PM that we extract for each step. At the end of the extraction, we add up all the different steps, and this gives us our component sum. And also at the end, we actually are doing a direct measurement of what we have in the vial that we hand over to the toxicologist. So this is percent difference between the component sum of our individual steps as well as our final mass. A value of 0 means that we are doing excellent and we exactly replicated. It's also a metric of mass closure. And you can see across all samples, we're averaging about 4 plus or minus 4%, which is very good. And with that, I would like to close and introduce Dr. Kent Pinkerton, who is going to talk about toxicological results.
Well, thank you. Thank goodness for engineers, because those of us who are biologists and toxicologists would be totally lost without them. I'd like to talk about the findings of using the materials which Dr. Wexler and Dr. Bein have discussed. Just a reminder that these materials that are collected are done under very elegant manners to give us 2 size fractions, an ultrafine particle size as well as a submicron fine particle. And these are collected in sufficient quantities so that we can actually do toxicological testing. One of the things I'd like to show here is just our study design. So what we're doing is once we have these materials, we can give an equal mass of each of these source-oriented materials by oral pharyngeal aspiration, which is just a way of having the mice, which are our subject for doing the studies, to inhale these on their own. Then what we are doing is we're looking 24 hours after the mice have aspirated this material and doing different types of biological assays. So the two that we really want to look at would be one to target the lungs, which is primarily by doing bronchoalveolar lavage, and secondly to look at systemic effects, which would be to look at blood elements. Also, in collaboration with Cord Anastasio, we've been able to work with these source-oriented particles, and for him to look at the activity of the particles alone, not in a biological system, but just simply what kind of reactive species may be generated through the presence of these types of particles. So just to give a bit of a brief definition for the endpoints, again, bronchoalveolar lavage is simply a classical way for us to easily look at the lungs, look at how they're responding to any kind of component that may be introduced into the lungs. So we typically will look at total cell number that we recovered by lavage as an indicator of injury. Whereas if we look at the different specific cell types that we find within the lavaged cells, we can also use that as an indicator of some idea of or signal for biological reactivity. Neutrophils are typically elevated in acute inflammation, whereas eosinophils might actually represent an indication of some type of allergic response that may be going on. We can also measure the protein that we recover in the lavage as an indication of cell injury, or looking at lactic dehydrogenase, or LDH, as an indicator of cell death. Within the blood, we can certainly look at different blood elements, and we won't go through all of them, but neutrophils certainly, if we see a depletion of those in the blood, we oftentimes assume that that is a suggestion of recruitment of those neutrophils into the lungs as a result of some sort of injury or acute response. And in terms of the reactive oxygen species, which Dr. Anastasio has looked at, when we look at reactive oxygen species and their presence, that certainly could be indicative of changes that may induce damage to DNA or cell membranes. So I wanted to show this bar graph as just simply an illustration for all the various source-oriented particles that we looked at over the summer using bronchoalveolar lavage. So along the y-axis is just simply a measure of total cell number recovered from the lungs. Along the x-axis is just the various source-oriented samples that we used. If you'll note that there is a black horizontal line across all of these bars, that is the control value, that for every source-oriented material that we worked with, whether it was ultrafine particles or submicron fine particles, there was always a control group that was run with that. So that black horizontal line represents the average total cells recovered from the lungs using lavage procedures from our sham control animals. And the light pink bar is for ultrafine particles. The dark or red bar is for the submicron fine particles. So you can see in just looking at these bars that a number of them are clearly above control values, while there are some source-oriented materials that are almost identical to what we saw in our sham control animals. Again, for each of these source-oriented particles, we gave an equal mass of the particles for each one of them, for both the ultrafine particles as well as the submicron fine particles. Now the next bar graph is in the same manner, but we're just looking at the winter particles that were collected. And here again, we see that black horizontal line across the bars as the control value, and then the light blue is for the ultrafine particles. The dark blue bars are for the submicron fine. And once again, you do see that there are differences. There are some particles where we see virtually no effects following their aspiration in the lungs compared to the sham controls. But one thing I would like to show or just mention on here, if you look in general, it appears as though for the winter source-oriented particles that we were looking at, for ultrafine particles, in general, they seem to have a greater response than for the submicron fine. That was kind of one thing that we looked at. But perhaps more importantly is to take advantage of what the engineers have done and now begin to compare and look at what's happening based on the source. So if we look at the summertime, Dr. Baina talked about residential cooking. And these oval bars that you see on oval circles around these bars represent the residential cooking source-oriented materials. And what we found here is in the upper panel, it's marked as circulating neutrophils. So the black bar represents control values for neutrophils within the circulating blood. And what we found here is with exposure to residential cooking, that the circulating neutrophils were significantly reduced or depleted from the circulating blood. In contrast, if you look at the middle panel, this is looking at the bronchoalveolar lavage, the cells that we recover from the lungs by washing, and there we saw a significant elevation in total cells recovered, and within that total cell number recovered by lavage, as shown in the bottom panel, there is a significant elevation in the total numbers of neutrophils that we're recovering from the lungs of these mice that were exposed to this source of residential cooking. We also noticed that for commercial cooking, not residential cooking, that within the bronchoalveolar lavage fluid, that there was a significant elevation in the protein levels, which again may be an indication of cell injury or cell permeability through that process. For winter cooking, again, looking at the source-oriented particles, we found very little effects in terms of pulmonary responses or systemic responses as indicated by looking at blood elements. Another category that we looked at was the winter biomass combustion. Again, Dr. Bain talked a lot about these materials and in essence that they could arise from different sources, but wood burning may be one particular example. And if you look at these bar graphs, again, the top panel is showing, again, cells that we recover from the lung by lavage, and that in this particular instance, in the winter, for the ultrafine particles, and I'm sorry, I didn't mention this earlier, but again, ultrafine particles are found to the right, that's the right set of bars, and then the submicron fine particles are to, I'm sorry, right, left, right, okay. To the left are the ultrafine particles, and to the right are the submicron fine particles. So what we're seeing here in the winter biomass combustion, that for the ultrafine particles that are from this source of biomass combustion, we saw a significant elevation in the number of eosinophils. Again, eosinophils are such a rare cell type that the control bar that's just to the left of that is almost indistinguishable. So a significant elevation there. In terms of other parameters over the winter biomass combustion, it's really in this submicron fine that we saw elevations in LDH, indication of cell death. And again, now in the ultrafine particles, an elevation in the amount of protein, an indication of cell injury or permeability. The next category is for vehicles, and again, this is during the summer months. And in this particular phase here, we found that for the source-oriented particles that predominantly came from vehicles, that we saw a significant elevation in total cells in the lavage material, that these were driven in large measure by a significant elevation in the neutrophils as seen in the middle panel, but also that these are accompanied by the presence of eosinophils that we also found in the lavage. What was striking, as noted in the bottom of this panel, is that we found virtually no effects from the vehicle mix, which contained more diesel than in this particular category, which is vehicles in the summer. What was interesting too is this is the work of Dr. Anastasio in which he is showing that these are vehicles in the summer. And again, in this particular example, the bars on the left, which are the red and yellow, that would be the summer. And again, red is ultrafine particles, yellow is submicron fine particles. And then on the right, those are the winter samples that he was looking at. But in this particular instance, he found in submicron fine particles that the relative degree of reactive oxygen species was significantly elevated, among other things. Now, I'll talk a little bit more about this as we go on, but I just wanted to also show that in the winter, we found that vehicles, this is again shown in the submicron fine particles, that there was a significant elevation in total cells were recovering from the lungs by lavage, and again that this is driven very much by an elevation in the number of neutrophils that are present. And that also we noted that systemically, I'm not going to show all of the data, but systemically, that there did appear to be effects that we could measure in the blood in the morning commute hours. Now, also in the next category, this is summer processed regional background material. And again, the effects that we were seeing here was in the ultrafine size range compared to the submicron fine. And again, we see elevations in total cells that were recovering from the lavage, again, driven by neutrophils, and also that we see the presence of eosinophils that are present as well. And in terms of the winter processed regional background, in this instance, we're seeing the effects in the submicron fine fraction, again, with a similar pattern of a total increase in total cells recovered by lavage, driven by both neutrophils and eosinophils. And again, now going to summertime, in this particular category, we were looking at the submicron fine particles, and we found that that summer metal categories showed a significant elevation in total cells, as well as a significant elevation in the protein levels found in the lavage fluid. Again, suggestive of cell injury and increased cell permeability. And to correlate with this, we found, again, through the Anastasio lab, that these particles by themselves, and this is shown here in the oval, this yellow bar, these summer metals, the same source-oriented particles that were used in the animal studies, also resulted in a significantly higher level of hydroxyl radical present that was generated by these particles in the submicron fine particles, the same pattern that we saw in the mice exposed to the submicron fine particles. So these are the conclusions that we have at this point for our studies, that certainly source-oriented sampling is feasible, that it represents a very novel sampling method, and we've been able to implement that very successfully. And that from this perspective, we found that different PM samples that can be attributed to different sources, and that we can also collect sufficient amounts of these particles to be able to do toxicity studies as we've reported today. I think another important conclusion is that the extraction method for these particles does matter. That with additional steps that Dr. Bine had talked about, we have been able to recover additional PM mass, and that these solvents allow us to recover additional chemical components found within the PM, and also, is most importantly for me as a toxicologist, to know precisely the dose that we're delivering to an animal in a toxicity test is absolutely paramount for us to be able to understand the actual effect of that material. Would also make the following conclusions, that from these studies to date, that there clearly are particles that are more toxic than others. And these are the ones that we seem to see as showing greater toxicity. That the particulate matter that contains metals during the summer, as well as vehicular emissions, have the largest biological response that we've seen to date. Winter PM, if we see highly processed materials, and as well as vehicular emissions and nighttime mixtures, they have the largest biological response. And finally, that ultrafine PM generates a greater biological response than the submicron fine, as I was showing. That in general, we just see that effect that the smaller the particle, based on an equal dose mass compared to larger particles, seem to have the greatest biological response. And so I think it's also important to point out that different particles, their toxicity is different in different ways. So that concludes the presentation, and we'd be happy to answer any questions that you may have.
Hello, this is Johan from ARB. Thank you. It was a very interesting and nice talk. I had a bunch of questions. I'll just ask a few of them, I guess. First is, I wasn't sure from your presentation whether or not the PM that eventually was given to Dr. Pinkerton was only solid, the solid PM that you ended up collecting, or did it also include liquid droplet aerosols, just from your extraction method?
So in the final steps of the extraction method, everything is reconstituted together. So it includes all the dry as well as the organic. Everything is put back together. The solvents are removed. It's weighed. It includes everything.
Is that answering the question? I think so. I think you said that both solid and liquid aerosols were.
Yeah. So yeah, it's all the solid it's all liquid organics. It's all the solid material, but in this size range, it's primarily EC. Okay, and then there are various water soluble things like electrolytes, ammonium nitrate, ammonium sulfate, and that's all given dry, but then it's resolubilized in saline before it's before the lavage is done, right? So that so those things are then are in the liquid phase. That the high water soluble stuff would then be in the same fluid that's given. That all the PM is suspended in. I think that's the right word.
Okay.
Yeah.
Thank you. Two more questions. I'll ask them both. Do you think that whether or not a particle is solid or liquid affects its toxicity? And then secondly, I just wanted to ask, your very last conclusion was that ultrafine PM generally elicits greater biological response than submicron fine PM. And I guess that result was basically the result is normalized by mass. If it isn't, what is the actual response of the amount out in the atmosphere of those two in a relative term?
Okay, great, thanks. Well, again, I think that both solid and aqueous particles can have a significant toxicity. And I think it's great that through the extraction methods that Dr. Bine has discussed, that we actually can recover far more of the mass, both the materials that would be in aqueous form as well as in solid form for our toxicity testing. Again, the materials, as was stated, they are lyophilized and they're in a dry state, so they must be reconstituted, resuspended. One of the challenges, though, and I think we need to understand this, is that when we're working with source-oriented materials that need to be extracted from filters or from special methods for collection, that to be able to have them back in their original size is not going to be a possibility. That there is going to continue to be issues with agglomeration, aggregation of the materials. In terms of the effects of the seeing greater biological responses in general, in terms of ultrafine particles versus submicron fine particles. That's based on mass. So again, it's interesting to see those responses, especially we saw that in particular for the winter samples. We didn't see that pattern as well established in summer samples. Again, in terms of actual exposures to ultrafine particles versus submicron fine particles, that would be very, very different. So I think we need to keep that in mind, that we don't see equal mass exposures to those different size particles in the environment.
And so one of the questions we didn't quite answer had to do with do we feel like the solid or liquid stuff is more or less toxic? And we don't have any information either way from the study. Yeah. The other thing, and you asked about the relative toxicity of the fine and ultrafine, or submicron fine and the ultrafine. But I want to emphasize here that we are giving the toxicity based on a per mass basis, which then, if you want to find out what the population exposure is and the population-based toxicity, then you have to weigh that with the prevalence, the concentration of that stuff in the atmosphere, which we did not do. That's a whole additional layer that has to come on top of this, right? So something may be very, very toxic, but at a very, very small concentration. But obviously we care about things that are highly toxic and also in a large concentration, because those are the things that are going to affect more people. So. Yes, we have all that. We have all that, right? Exactly, yeah.
One other thing that I would simply mention is just, it is interesting because as we reconstitute these particles in the different size fractions, again, when we do dynamic light scattering just to see what the sizes are, again, we're seeing that they're in somewhat in the same size categories. Again, ultrafine particles tend to be a little bit smaller than the submicron fine. But again, that toxicity, I think, is still can be based on something that has to do with their unique size, even though they're in an agglomerated state.
I want to say one more thing, yet again. So going back then to the relative concentrations and relative toxicities of the different things, yes, we have the information for one site in Fresno where we measured, but I think what you really need to do is look at the inventory, because what you care about is, the population averaged toxicity over a region, and we were near certain sources and far from other sources, so we're not doing you shouldn't take the results that we have and extrapolate to, all of Fresno or all of San Joaquin Valley either. The emissions inventory is a much better way to do that.
Okay, I guess now we have a question from our webcast audience. It's from Jim Mason, who is from the Integrated Health Services Division of IBM Research. And the question is, can you compare your findings to a real-life example? PM 2.5 counts in Beijing were above the 500 micrograms per meters cube range in January. Do you have to know the source to make a judgment? Is there more to say than this is bad?
Take it, Kent.
Okay. Well, I would say that certainly the concentrations of PM 2.5 counts that are illustrated here are not that unusual. We've had the same thing happen here in the Central Valley in 2008 for our wildfires, where we had a tremendous mass that was present there. And in terms of the effects there, we clearly did see significant biological effects due to wildfire emissions. But in terms of trying to, the findings for real life examples, again, I guess I would turn to those, the California wildfire experience, where we saw significant effects that were occurring at those particular concentrations. Do you have to know the source to make a judgment? I think it certainly helps us in understanding the mechanisms of toxicity associated with particles, to know what that particle is. To have it largely as an unknown particle based on mass, as Dr. Wexler had pointed out earlier, really makes it difficult for us to be able to get a decision to help us to understand why we see toxicity at sometimes with a certain mass of particles, and then with the identical mass of particles we see absolutely nothing. Even within the studies that we've shown today, as I mentioned, some of the ChemVol samples at an equal mass concentration showed absolutely no biological responses for those bioassays or those endpoints that we chose to use in contrast to others.
Yeah, I also want to say in response to this question that there are numerous epidemiological studies establishing that PM2.5 increases morbidity and mortality. Okay, this study that we just performed here is in no way displacing that. Okay, that is PM2.5 is bad stuff. Okay, the question here is a little more nuanced. The question here is which are the sources that are primarily responsible for the toxicity, and even with our study, which we used a lot of different endpoints, isn't necessarily comprehensive. For instance, we don't have cardiovascular endpoints well represented in this study. We had limited budget, and we did what we could within the budget. So more work needs to be done to really completely characterize the full range of toxicity from the different sources.
Hi, it's Mike Wang. I have a question. A lot of your study centers on the ability to use your high-vol sampler and understand the source that was in those high-vols. Were you able to ever confirm using any tracer analysis the accuracy of the source attribution? And then secondly, in Fresno, there are a lot of times when there's stagnant conditions. Was that a problem? How did you address it?
Yeah. So I think that Fresno is one of the most difficult places to perform the study. We've done, for instance, sampling in Pittsburgh using the same kind of instrumentation, and there you have these prevailing wind directions. The wind comes from the coal-fired power plant or from the steel mill, and you nail that. You can see that. In Fresno, the air's kind of mushy, right? Especially in these stagnant conditions, it's kind of floating here and it's floating there, and so that made the study more difficult for us to do. We had to be able to catch these different pockets of air coming by with different sources in them. So that's sort of one answer to your set of questions. Fresno is a difficult place to do the study. Another aspect here is the tracers. Now we did not introduce any tracers, but the fact that we were able to measure many different chemical composition components within the particles in the atmosphere, those are the tracers, right? They're inherent tracers. And we've seen this in all these different cities that we've worked in, that there are clear tracers for different stuff. And you can, one of the many indications of that are the wind rose plots that Dr. Bine showed. We had no information about wind direction when we did the study. It was completely based on chemical composition. But sure enough, you look at what direction the wind is coming from when you see different compositions, and you see that there are clear directionalities, which makes sense when you start thinking about the chemical composition, the time of day, the wind speed, that there are certain different sources that are primarily responsible for the different stuff that we collected. So Pat, should we read a question? So Pat, are we taking questions off the printout now?
Yeah, we're taking questions off the webcast right now.
Okay.
And this one's for Kent. It involves one slides on there.
So who's going? Are you going to read the question?
Yeah, I'll read the question. Yeah, on slide 42, you say that there are no effects from the vehicle mix with more diesel. Are you saying that it didn't matter whether there was diesel vehicles or not, and gasoline diesel sources are having approximately equal effects on lung, BAL? And this is from Ken Kimura from BP.
Well, I'll start with, and again, in this particular instance, what we found is that in comparison to no, I think it's right here, yeah. So in this particular slide, vehicles in the summer showed a significant effect for biological responses within the lungs, but we used an equal mass of the chemvol that had more of a mixture of vehicle with more diesel, and we did not see an effect. So we're not necessarily saying that from the perspective that these materials may be less toxic, but at least for the time frame that we used, which was a 24-hour post-exposure, for this particular mixture, we did not see any type of effects that we were able to note with just vehicles alone in the summer. Again, this was for, in this particular study, it was for only the ultrafine fraction that we saw these effects to occur.
I think Keith would like to address some of how we differentiate vehicles with and without diesel and in our study.
Yeah, so the ChemVol that you're referring to as far as not showing an effect for diesel was ChemVol 3, I believe. And the predominant PM component that we used to assign that ChemVol was a relatively pure EC containing particle. We're not seeing a whole lot of signs of any OC in that particle, and as such, we tend to associate that more with diesel emissions versus vehicle emissions, where vehicle emissions tend to be more a mixture of both elemental carbon and or organic carbon. Obviously, there are other sources of EC containing particles in the atmosphere beside diesel, and we assign this to vehicular emissions with a kind of a diesel enhancement because we're seeing fairly pure EC particles, and based on the temporal analysis and the wind directional analysis, we saw a high correlation with the morning and rush hour commute, as well as a high correlation with the Yosemite Freeway. And our best guess is that this is vehicular emissions with some enhancement in diesel. So I'm not sure if I answered the question, but that's the way we typically try to differentiate between gasoline-powered and diesel emissions, but it's not perfect. Question?
This is Tony Van Kuren, and actually I'm with UC Davis. In the definition of ultrafines and submicron particles, I get the impression that submicron particles include ultrafines, and so the ultrafines are a subset of the submicron. Is that a correct interpretation?
That is not correct.
Okay.
So the ChemVol it removes everything above roughly 1 micron, and then there's an impactor, which then removes the particles that have an aerodynamic diameter larger than 170 nanometers onto the puff, the polyurethane foam substrate, and the particles that are smaller than that then end up on a backup filter.
Okay, so the submicrons and the ultrafines are independent
Yes.
Materials?
Yes.
Okay.
Linda Smith, ARB. In your last slide, you say that the highly processed fraction gave you a higher signal for winter PM. So can you speculate why you think in the winter you get a high signal, but summer you get a lower signal?
Again, I think the highly processed, we need to probably have Keith tell us a little bit about what the composition is. So this is just kind of the background. This is the transformation of particles and just the aging of particles in the atmosphere.
So let me give a shot at it, and then you can embellish my shot about that. So in the wintertime, of course, there's more, it's colder and it's more humid, and so even though the photochemical activity is less, there's more material phase partitioned to the particle phase, right? So we know that in the San Joaquin Valley, in the wintertime, ammonium nitrate is huge, and many other secondary compounds are huge there. So in addition to that, the inversion is lower, so it concentrates a lot of material anyway. So that's sort of one aspect of the answer.
I think another aspect will be that the background PM, the sources of the background PM that are being processed are different in the winter than they are in the summer. A large component of that, like I said, was agricultural emissions, and these are highly seasonal dependent. In the wintertime, when agricultural season is low, a larger fraction will be from vehicular emissions that are trapped in the valley. As far as a particular chemical composition differences between what we saw in the summer and what we saw in the winter, in the summer, most of what we saw was ammonium nitrate. Whereas in the winter, we saw the ammonium nitrate, but we always see these highly oxidized organic fragment ions that we didn't really see in the summer. We see a lot of different kind of organic ions. We see elemental ions, atomic ions, fragment ions, cluster ions. And we can tell basically what they're made of, the carbon to hydrogen to oxygen ratios. And then in the winter, we saw a lot more oxygen, which is indicative of these highly oxidized particles. And we didn't really see as much as that in the summer. And in the summer, the bigger indicator was this overwhelming ammonium nitrate signal.
Pat. It's a follow-up. Thanks. Yeah, we have a follow-up question from Ken Kimura from BP. He's the one that asked the questions earlier about the no effects from the vehicle mix with more diesel. And the question is, having a biological response is one thing, but what is the impact on a toxicity scale on the measured particles based on the volume sample to get the PM sample?
Yeah, this is a complicated, interesting question. And it had to do with something that I alluded to earlier. Oh, we're having microphone swap. Something I alluded to earlier about we did all these toxicity tests on a per mass basis, but then you have to weigh it by the actual concentration of that stuff or emission of that stuff into the atmosphere. Now, in the studies that we conducted, we have to be very careful about this because we may have, there's some of the samples that we collected had a lot of material and some had a little material, but that isn't even necessarily indicative of how much of that stuff was in the atmosphere because we were only able to sample material that was well separated. Okay, so it may be the stuff for a particular source may be prevalent in the atmosphere, but then well mixed with other sources, so we're not able to separate it out, right? And so we were constrained to collect onto these different source-oriented chemvols by when these sources were separated from other sources, right? So, and that is an independent, or not independent, but anyway, it's related, but nearly independent of how much of that material is in the atmosphere. The vast majority of the material that we collected was collected on Chemvol 9 and Chemvol 10. Those were the ones that were run, the Chemvol 9 was primarily run in the daytime, Chemvol 10 was run when we didn't know what was going on, and that is a complex mixture of all the other stuff that was collected in each of the different source-oriented samples. So I understand your question. I would like to know the answer to this too. It comes back to what I was talking about earlier, which is you need to sort of take this information that we've collected here and kind of resolve it with the emissions inventory and meteorology and maybe doing some grid-based modeling to figure out the population-based exposure of each of the different sources. And then from that, the population-based toxicity for the endpoints that we looked at, but not for, there's other endpoints too. The study was not completely comprehensive.
And I think just to add to that, as Tony has mentioned, is that if we're just simply looking at toxicity based on mass, that these are the types of studies that we can begin to address those type of issues based on source. But again, as Tony has very clearly pointed out, that is not necessarily the kind of exposure that one receives in a real-world environment.
Hi, I guess we have a final question from our webcast audience, and this comes from Hal Tabak from Carlsbad, California. And the question is, are you aware of microscope chemical imaging for near real-time, allowing the generation of a spatial and temporal map of pollutant source impacts?
I don't know this exact terminology. I know that we have colleagues at Pacific Northwest Laboratory in Washington State that do microscopic analysis of substrates, but it's not in real time. It sounds something, I don't know this terminology, so I don't know. Keith, do you know? Or Ken? No? So I don't know, I do not know this terminology and how it would relate to this study. Sorry.
Okay, thank you, Tony. I guess, are there any final questions? I guess if there are no more final questions, I'd like to thank the audience for their questions, as well as the webcast audience, and thank our three speakers for a wonderful talk today. Thank you.